Welcome to another problem of physics desk in Coulomb's law of electrostatics. This problem is very much similar to my previous problem with only a small change in the condition. In my previous problem, we have talked about Moon orbiting Earth in a circular orbit wherein both Moon and Earth get an identical charge Q which cause them to move apart, and Moon therefore entered into a higher circular orbit around Earth. So there the question was, what should be the magnitude of charge in order for Moon's orbital radius to achieve a desired value, say 4 times or 5 times or n times. Here the question is framed slightly different. Now our requirement is that Moon should totally escape Earth's orbit. For that, what should be the minimum value of this charge? So let me read out the problem. Consider the case of Moon orbiting Earth in a perfectly circular motion. What should be the minimum amount of identical charge that, if given to both the bodies, cause the Moon to completely escape Earth's gravity, unlike in the previous case where it still remained in the orbit but moved to a higher radius, assuming both objects has point size due to their large separation and Earth's position as highly stable due to its very high mass. So we have the Moon in a circular orbit as shown in the figure with radius r and orbital speed v initially. The necessary centripetal force comes from the gravity on it by the Earth, which is given by Fg. Now both the bodies acquire a charge of q coulombs each. That means Earth as well as Moon are given q coulombs. What happens? Both of them repel each other, as a result of which the condition is that Moon should escape the Earth's orbit totally and should not move to higher orbital radius. So the electrostatic force Fe on Moon is in a direction opposite to that of the gravitational force, which is Fg. So according to the problem, Moon must break away from Earth's orbit completely. So what should be the value of the charge so that such a force is created? The basic condition required for any object to escape orbital motion is that centripetal force acting on it must be reduced to 0. So the centripetal force here acting on the Moon, which is caused by Earth's gravity, should become 0. Simple. So for that, the gravitational force should be equal to electrostatic force. So Fg is equal to Fe, which implies Gmm by r square is equal to k q1 q2 by r square, where m and m are mass of the Earth and mass of the Moon respectively, and q1 and q2 are the charges given to both the bodies. Here the charges are identical as given in the problem. So Gmm by r square is equal to k q square by r square, which gives us q square is equal to Gmm by k. R is totally eliminated, so it's not at all required. So that makes it q is equal to square root of Gmm by k. We know the value of G, which is universal gravitational constant, 6.67 into 10 power minus 11, mass of the Earth 5.97 into 10 power 24 kg, mass of the Moon 7.34 into 10 power 22 kg, and Coulomb's constant 9 into 10 power 9 in free space, giving us approximately 5.7 into 10 power 13 Coulomb, which is a very large number. So if both Earth and Moon acquire a charge close to this 5.7 into 10 power 13 Coulomb, they repel each other and break the orbit. Thank you. It's a very simple and easy problem.